in other languages. And in fact, today, the main challenge for the intelligent systems to be really intelligent is that they still have to master interpretation of text. The machines, even the most intelligent ones, they still cannot interpret text. Once they are able to do it, then we'll have a completely different scenario of science and technology and of the society as well, because you have machines replacing humans in almost all the intellectual tasks. And a very important application that has just been launched actually last week was this chatbot, this robot, this intelligent robot that was launched by OpenAI, which is an open institution for artificial intelligence. And it's the machine or the robot can do amazing things. They can produce text that are undistinguishable from what humans do. And in fact, if you read this article in the New York Times, the journalist was saying, German Lopes, he was saying that he has always heard about the promises of artificial intelligence, that the real intelligent systems will be coming in the next 5 years, So this is always being predicted. There's still some more years to come. But now we got to a position with this tool that we are really already seeing very intelligent robots, because these robots can do things with languages that are almost practically unbelievable. At least it was unbelievable a few years ago. Later on, it will be clear why in lecturing material sciences, I'm starting with language. So I'll come back to that. So I will start in the lecture. My first topic in the lecture is knowledge discovery. Then I'll be talking about sensors and biosensors and the using of machine learning and natural language processing in material sciences. And then I'll wrap up the lecture with a new paradigm for creating knowledge and transmitting knowledge. So I started with knowledge discovery, which is a topic which has been around for more than decades, 2 or 3 decades in computer science. And it was created when researchers realized that with so much data available in databases, in text databases, in the literature, that they could dig knowledge from these databases. Today, this area is being taken to a new level. As we have more and more sophisticated natural language processing tools, we can do things in knowledge discovery now that would be impossible a few years ago. We can inquire the literature, we can mine the literature and find things, mine thousands of papers at the same time, and then find information there. I'll give an example later on. But knowledge discovery is going to be the ultimate application of artificial intelligence. Artificial intelligence that has many different areas: natural language processing, robotics, computer vision, and so on, and also machine learning, which is the most important in material sciences. Machine learning today is used for data analysis. I'm going to show examples. It's also used to producing semi-automated surveys, and it's used for materials discovery. You can discover new materials, you can discover new materials properties using machine learning, and all of these methods will converge into knowledge discovery. So you may ask whether many people in the world are paying attention on the ways the materials research is going to be done in the future. A few years ago, around 40 scientists were gathered in a hotel, and they had the following task. They had to come up with the idea of what would be a platform for materials research of the future. So they had to say what is coming in this research of materials. And it's interesting that they came up with a concept, a platform, which had 2 branches. On the left-hand side branch, you have data knowledge data and knowledge assets. So here is mostly related to data and all the problems that you have with the data that you have. You need to worry about integrity. You need to do intelligent search in the data. You need to do intelligent visualization and so on. On the right-hand side is the other branch, which is automation of science. Because if you need a lot of data, when this data is to be produced by devices, you need to automate data collection. So you need to automate experiments, simulations, and for that, you also use machine learning. You have to do scale bridging because in many cases, you want to study materials from the nanoscale to the macro scale. So you need experiments, you need infrastructure and instrumentation to do this scale bridging as well. And obviously, these are on the left-hand side data, on the right-hand side how to collect data, and you need integrative approaches. Another thing which came up from their paper, they produced a paper out of their meeting, was a list of 16 keywords or key terms that they think will be very important for the future. You can have a look at these terms here, and you realize that most of them are not related to materials per se. They're related to data analysis, they're related to language processing, to software infrastructure, to visualization. So it's mostly from one side, machine learning in other artificial intelligence systems, on the other side, automation and data analysis and data management. You see, these are the 16 key terms that these authors thought that would hold a lot of future in material research. And they are completely different from what we do today. The keywords that we use in our research are entirely different. And therefore, we have to be aware that a revolution is coming in the way material research is done. For sensing and biosensing in particular, if you want to go from sensing to diagnostics, and this diagnostic could be clinical diagnostics, it could be diagnosis of the health of buildings, it could be diagnosing in terms of monitoring the environment. So if you want to do it, you need a number of prerequisites. You need fundamental research in several different areas. You need technologies for sensors, biosensors, and instruments for measuring. You need data repository. And obviously, if you're going to do monitoring, or if you're going to do monitoring of the health of a person, or monitoring of the environment, you are going to need Internet of Things as well. So things must be connected to the internet, and obviously need artificial intelligence methods. And then you can apply this, for instance, for diagnosis of human diseases and animal diseases. You can monitor environmental pollution. You can do drug testing discovery. You can use this in food and agriculture. And also you have to worry about the outcomes, because in a system like this, there will be many products. Some of the products will be scientific advances. In other cases, there will be products to be sold, to be transferred to the society. But there is also another important aspect, which is education outreach. Scientists today, they need to do outreach activities. We need to go towards society and explain to society the importance, the value of science, the value of technology, because this is something which transforms people's lives. And in terms of using machine learning in other artificial intelligence systems for data analysis, we can now conceive a data processing pipeline. You have to do data collection. If you can do it automated, it's better, even better. If you're going to interact with the user, you may visualize the data in different ways. You may do clustering and unsupervised machine learning just to try and explore the data. But in many cases, when you're doing a diagnosis, you need to do classification. And for this, you use supervised machine learning. So there are several issues to be taken into account. For instance, when you're doing data collection, you have to realize that if you're going to use supervised machine learning and to do classification, you need to have balanced classes. So the number of experiments in each class must be the same. So if you are, say, testing someone for a disease, and it's yes or no for being sick or not. So if you are using machine learning to treat the data, you must have the same number of positive cases to the same number of negative cases. So the classes must be balanced. So for you to apply supervised machine learning. So there are a number of issues that must be taken into account when you are doing a pipeline like this. So, and then there is another thing that you can do when you use machine learning. You can go beyond calibration curves. You can go beyond calibration curves. So today in analytical chemistry, for instance, we tend to use calibration curve when you have just one variable. So the signal depends on a variable. Like in this case, you have a signal with a capacitance. It varies linearly with the concentration of a given analyte. So this is your analytical curve. So that's how we do analytical chemistry as well. When you have many variables, we do multivariate statistics for them. But this is limited because if you have an electronic tongue or electronic nose, when you are comparing different types of liquids or different types of gases or vapors, for instance, if you are testing different types of tea or different types of milk, you cannot have calibration curves. But if you use machine learning, you can have calibration spaces. And these calibration spaces, they are similar in concept to the calibration curves, but they are much broader. They are much more flexible in terms of the data that you can use. And these calibration spaces may have many dimensions. For instance, I just represent a machine, a calibration space which has 3 dimensions. So as it has 3 dimensions, I can represent in a graph like this. And how can you read this? Well, I read this the following. It's a 3-dimensional calibration space because it depends on 3 features or 3 variables. So you measure your quantities for these 3 variables, and then you can see the regions where you have the different classes of your samples. So with the 3-dimensional space, you can use this graphic, but usually if you have more dimension, we can use a matrix representation, as I'm going to show in an example. Just to summarize this new concept, you replace calibration curve with a multidimensional space, so it can go beyond 1 or 2, 3 dimensions. You replace equations for the calibration curves by rules of decision trees or abundant forests. So you use a machine learning algorithm which has rules so that it can explain how the data are classified. The number of dimensions is the number of features that you have to use to explain the data. The number of rules, the minimum number of rules, is the number of classes that you have to use. So if you have, say, yes or no, the minimum, so you have 2 classes only, so you need at least 2 rules to explain the data. And then you can use this for many applications in which data analysis is a very hard task. This is a case of trying to diagnose mastitis in cows. So the mastitis in cows you can diagnose by, for instance, using a biosensor to detect bacteria like Staphylococcus aureus, or you can use an electronic tank. Electronic tank does not have specific biosensors or specific sensors. What an electronic tank does is to measure the overall electrical properties of a liquid with different sensors, and then you combine these different electrical responses on a finger, like a fingerprint of a given liquid. The thing is, electronic tanks are so sensitive that you can distinguish minute changes from one liquid to the other. Like in this case, we use milk from cows, some of which had been naturally infected with mastitis. And we could, and in some cases, one cow had another which was much more infected than the other one. So you could distinguish when the milk came from one other from another other. So you could distinguish this milk from a milk of a healthy cow. So indeed, we could use an electronic tag to, by just analyzing the milk, we can predict or we can say whether this cow has mastitis or not, or even if one other of one cow is more infected than the other. When we do this with machine learning to analyze the data of the electronic tag, we could explain the data by using a multi-calibration space which had 6 dimensions. So 6 dimensions means that we you need to use 6 features. In this case, there are 6 different frequencies in your impedance spectra. So we measure impedance spectra for the milk, and then we use the whole data with this machine learning process to explain or to categorize the milks from different types of cows. And also for this, we use multi-calibration space of 6 dimensions. But we can do more complicated things. For instance, in this case, we analyze saliva of volunteers or cancer patients, cancer of the mouth, and we could distinguish when the patient, whether the patient had cancer, oral cancer or not, and then because we use this concept of multidimensional calibration space, we could find which would be the most important frequencies at which we had to make the measurement with electronic time, but also we could combine the data from the electronic tank with clinical data. So we had information of the patients, whether they had whether they smoke or not, or whether they have problems with alcoholism or not. And what we found in this particular study is that one of the most important parameters was whether the person had issues with alcoholism. Unfortunately, the number of patients and volunteers was only 27, and therefore not many. We cannot just make a definite conclusion that alcoholism is an important parameter or factor for oral cancer, because we didn't have sufficient data for that. But nevertheless, the approach shows the power of analysis like this. So now we hope that we can extend this study to, say, hundreds of patients and volunteers, and then we will be able to determine the most important factors that lead to cancer in a patient, oral cancer. The other application that we have is just to detect the SARS-CoV-2 using saliva in only 5 minutes. And the sensor that we produce is a biosensor made with gold nanoparticles covered with antibodies that can recognize the spike protein of the virus. And so once the saliva, when the virus get in contact with these nanoparticles, if the nanoparticles will aggregate around the virus, and we see that with microscopy, electron microscopy, and we also calculate, we do computer simulations to see what happens when the nanoparticles aggregate. And when the nanoparticles aggregate, they change color, and we can see if the viral load is high, we can see a very clear color. So yes or no is very easy. But if the person has just got COVID and the concentration is very small, then the change in color is small. So what we do now, we take a picture of the vial with the sample. So we get this tube with the saliva. We take a picture, and then by taking a picture, we process the images of the picture, and use now machine learning to predict whether, not only whether that person has been infected with SARS-CoV-2, but also the viral load, because we do a calibration with known concentrations of viral load with the images, and then we use this multi-dimensional calibration space, so that, and we did 6 dimensions calibration space to explain or to determine the concentration of the virus in saliva. So this is really an exciting thing, because we can, without any instrument, you just use your camera and take a picture. We have an app to process the image, use machine learning to process the data, and then you know the viral load if you have been infected. So this idea of using images for monitoring or for doing diagnosis is a key thing in our research, because in the future, all we want to do is not use instruments to do diagnosis, not use instruments to do monitoring. We just take pictures, or we film, we have a video with a camera, and then we'll be able, by just processing the image, we'll be able to do the monitoring. So this is an example of a mechanochromic sensor. So this is a sensor, a 3-layer sensor, in which as you compress or you stretch, it changes color. The change is so big, the change in color is so effective that you can use this system under sunlight. You can put on clothes, on clothes, and you can use underwater as well. So it's a very clear change in color. So what we did was the following: we did experiments with mechanical tests in which we measured the deformation and the strain and the stress, and then we took pictures. We filmed as the measurements were done, and then with those measurements we can later on just stretch or compress the sensor, and then by just taking the picture, we know the strain and the stress of the system. And this is just a short video which shows that that's the deformation predicted by the equipment, and that's the predicted one. So you have a very good agreement between the predicted and the actually measured strain. So you can, by just filming, we can determine the strain, and because this system is elastic, we can determine the stress as well. So that's a very easy way to determine the stress on the strain without using any instrument. You just film it and then use a system for machine learning system for processing and processing the image and doing the classification. So I said that machine learning is being used for materials discovery. I'm going to show 2 examples from colleagues of mine. The first one is from glasses, to discover new types of glass. So they had a database with more than 45,000 glasses from inorganic oxides. And then they had the refractive index and the glass resolution temperature. And then they used this information to design new glasses, which would have high refractive index and low glass transition temperature. So of the candidates they found, they actually produced the glasses. And as you see the numbers there, the glasses 1 and 2 had properties which are very similar to the predicted ones. So this is a way that rather than you doing experiments by trial and error, you can actually predict the properties of a material, in this case glass, and then you can synthesize the glass according to the predicted values. And that's another example now of knowledge discovery. With knowledge discovery, so you combine machine learning and natural language processing. With these, you can mine thousands of papers. So in this case, they mined over almost 11,000 scientific articles, which were articles indexed according to carbon functional materials. And with this system, they could identify which are the precursors and synthesis methods to produce these functional materials. They could find correlations of what are the most used precursors to produce the materials for agriculture, for fuel, and so on and so forth. So you see, they, I would say, between inverted commas, they read almost the system read almost 11,000 papers and got useful information. I mean, even though it's a very sophisticated application of knowledge discovery, you may also argue that it's very limited. It's very limited because the machines cannot interpret text. And that's why the recent developments on natural language processing are so important. Because in the future, we will probably have a machine that you will ask a question, the machine will go to the literature and find the answers for us. So that's going to change completely the way we do material sciences. And biodiagnosis will be able to combine data, not only from one patient, but from many patients. And more than that, you can combine clinical data from sensing, from reports, from images. You see, when you use electronic tongue and also clinical data from patients, we were sort of using more or less this, but you can do much more. So if you have a lot of data, then you can even apply deep learning, because deep learning requires a lot of data. But then you can produce a diagnosis system which is much better. So now we can think of a new paradigm of producing knowledge. So far, all the knowledge that's produced has human intervention. But very soon, the machines themselves will be able to generate knowledge. And what's required for that? What's required is a convergence of two big movements. On the left-hand side, you have the big data movement. So you take a lot of data, use machine learning to transform information knowledge. And on the right-hand side is the natural language processing movement. So you are teaching the computers to interpret text. So once the machine is able to interpret text, we'll be able to have machines producing knowledge. And we need a lot of things for that, especially data. You need materials, you need new methods for machine learning, and so on and so forth. So I'll finish off by saying that the machines of the future will be able to develop tasks or to perform tasks, including intellectual tasks, much better than ourselves, than the humans, and this will change completely the landscape. And a sort of provocation for the young students there, young researchers, so when you're solving a problem, you could ask yourself how an intelligent system will solve that. So how can you solve a problem using an intelligent system? Because in many cases, if you have a robot which is clever, you may solve the problems in completely different ways that we would do. So I have a long list of collaborators and funding agencies, and I thank you for your attention. Thank you very much, and I'm really looking forward to your questions. Thank you.
Speech, I think you have information related to your artificial intelligence progress, and also you give us a glimpse how this kind of AI can be discovered by the humankind, and the future itself could be shaped by the artificial intelligence itself. And actually, I'm really intrigued with your question that you put in your last slide, which is society being prepared for that? So I mean, we are really reluctant with the kind of movement. I mean, if we move from the third industrial revolution to the fourth industrial revolution, there will be many disruption on that. And I do believe with this paradigm that you share to us, it will also shape our future. And of course, ladies and gentlemen, we will move to the Q&A session. If there is any question on the floor, please raise your hand and you can express your concern or anything related to the topics. So please, anyone? All right. I have Miss Christine here. Please.
Thank you for giving me opportunity. Thank you for your presentation. It was really insightful. I would like to ask because as far as I know, in Indonesia, machine learning and NLP is not really developed that much recently, but some modelings are still ongoing. And I would like to ask about the machine learning because machine learning comes from gathering a lot of data, and with that comes multiple steps until we get the final results or recommendations or any questions that we think it's finished as machine. So my first question is, if we want to filter some of the variables or parameters that maybe we don't want this and maybe we want that, can we make the machine unlearn some of the things that we have put before? So can we make the machine step backwards? That's my first question. And or maybe we have to erase all the history and we have to start over. That's my first question. And the second question, maybe from your experience, because I think that was very nice experiments about the machine learning. I was curious as to what could go wrong with us creating a machine to learn to give birth to a new knowledge. Exactly the fifth step of this paradigm. Thank you.
Thank you very much for the questions. I think it's really essential that any country starts to develop their expertise in machine learning and natural language processing. In your case, you have to do it in Indonesian, in addition to doing things in English. So it's absolutely essential. And I don't think we erase the history of the past, because we have to use a lot of data from the past. We'll have to check whether that data is reliable. That's always a big problem with machine learning, because if you don't use the right data, if you don't ask the right questions, you are not going to get good results. And indeed, one very important thing to be aware of is that machine learning is today very limited to classification tasks. It's very good to do classification. For instance, for facial recognition. So if you have sufficient data and processing power, you can do it much better than humans. So you can classify people by their faces. So that's a classification task, which is really a sophisticated one. And it's really well done by the machines, because you have sufficient data, and that data covers what you need to recognize a person. Another example of very good application of machine learning, which is also classification, is for diagnosis based on images. So in some areas in which you have a collection of images which are representative of all possible, say, diseases or types of diagnostics, so machine learning is already much better than the experts, even the specialists. So whenever you have sufficient data, processing power, and you are doing classification, machine learning is very good. Machine learning is not good, though, for tasks that requires interpretation. So that's why if you want to interpret text, then machine learning is not very good. That's why there is tremendous room for development, because we're still far away from the day that the machines will generate knowledge because the machines today cannot interpret text. As for the second question, if you could remind me the second question, which one was that?
Well, my second question was, with all those data and process that we create machine learning, what could probably go wrong? Because machine learning can actually make new knowledge from what they have learned.
Okay, that's fine. So first, I think there are two important points in our question. One is that we need to make sure that we don't get wrong answers, because either the methods used were not proper or the data that we used were not proper. We also have to worry about bias. So that's as everybody knows, from the problem with social media, bias is a big problem. So we have to go around that. So these are very important points. And as for new knowledge, there is a big debate in the literature as to whether artificial intelligence systems are really creative in the sense that they can create new knowledge. I argue that they can, but they can in a very, say, peculiar way. They can create new knowledge by receiving instructions that they should create new knowledge. And that's an interesting thing. So, because, for instance, like art. So if you ask a computer to do a new painting, you may just get all the paintings in the world, combine them and bring paintings which are different from everything else. So you see the the system will come up with paintings which you could never see anywhere, because the computer already checked that there was nothing like that. So you may think, oh, the system is very creative because it created something that did not exist. And it was not a very clever thing that the system did. The system just followed the instruction, check what is available, and produce something which is different from what is available. That's with these two simple instructions, you have a system which seems to be very creative. So the machines will be able to create new knowledge by getting these instructions. And obviously you can think that after some time, the computers or the machines learn to create instructions. So you can also instruct your machines to create instructions. So you see, you have like a snowball that will increase and increase. At the end of the day, you're going to have machines which will be much more clever than the humans, because they have a processing power which is not possible to compare to what that we have now.
Answers, and I think it's completely answered the questions. We still have one or two more questions for the audience. Is there any question? Okay. Yeah. Thank you very much for the opportunity, and thank you for the excellent presentation, Professor. So I will just close, Professor. How do we calibrate the biosensor, or how do we know the biosensor is still good to use so we can get a good data for the machine learning?
Yeah. So thank you very much for the question. So the way we do is the normal way. We have to see whether it's reproducible and whether it can get the right result. That's not different from what we do in our normal lives in analytical chemistry. So we have to use the same procedures, test whether the results are reproducible, and the bad news here is that you usually need much more data than we are used to producing. For instance, in analytical chemistry with biosensors, In many cases, we just do measurements in triplicate or triplicate or 5 times, so 5 repetitions. Whereas for employing machine learning, in many cases, you need many more repetitions. So this means that by need, you are going to be testing your biosensors. Obviously, we know that biosensors may degrade and they may change their response, and we have to check that as well. But in this particular case, if you use a system which processes the data, you may follow the degradation. You may sort of change the calibration. So you can use this information as well when you are treating the data. So it's an extra layer of possibility. But again, I mean, if you have degradation that you don't know how to control, or if the biosensor stops working, then you cannot use. And obviously, as in other cases, if the data are not proper, then you are going to have the wrong results. So that the checks and balances that you need to have are very similar to what we already have for biosensors or sensors.
Yeah. Any response? I think it's all clear. Yeah. Okay. Thank you, Osvaldo, for your answers and also for the question from the audience. I think we still have one more last question, maybe, Prof. Osvaldo, if you don't mind. Hello, Prof. Osvaldo? Can you hear us? Hello, Prof. Osvaldo?
Yes, I hear.
Okay.
Yeah.
Okay. Is there any one last question for the from the audience? Anyone? All right. If done anything, so it could be come from me as well, actually. Well, I'm really a big fan, to be honest, related to the artificial intelligence because it's related to our futures, right? But when we talk about the kinds like the futures of its destiny itself, it means that when we want to develop the AI and also machine learning and such technology, we need consider in two perspectives. The first one comes from the hardware, because we need still to hope for to the supercomputers and the quantum computers to process more data in the short time. And the second ones come from the role of the material itself. I want to push you on that point, Professor Osvaldo. What do you think about the best material for the artificial intelligence and other technology that's related to the machine learning? I mean, is there any specific material that we want to discover in the future to, strengthen and also to bolster this kind of artificial intelligence development? And if we found that kind of material, so how it would be in the futures? Because as we know, like now we are in the computer age. We know that when we know that Taiwan is on the crisis with China, so the kind of silicon and also semiconductor is on a shortage, so it will hamper the production of the technology itself. So what do you think about the future of this artificial intelligence related to material solutions? Thank you.
Okay. Thank you very much. Two very interesting questions. Everything that I talk about in this lecture today is for classical computing, not quantum computing. So in the sense that there's normal computing. When quantum computing becomes a reality, then you're going to have a much bigger ability or much higher capacity to process data and to much more memory, which means that these applications that we have seen so far were going to be upgraded. So probably to be much easier to produce intelligent systems when you have quantum computing because of the sheer capacity that's going to be much larger. So that's one thing. And second, everything that I talked about here is machine learning via software, only software. I didn't talk anything about machine learning via hardware, but this can also be done. You can also use hardware. So that will need to be a special material. It's not going to be silicon. So you may have, materials that can be used for neuromorphic computing. It can be polymers, it can be phase change materials. So this is a very embryonic, at the embryonic stage, so that there's not much in the literature. But once you have machine learning in the hardware, then the possibilities are going to be much bigger, because then you can have robots which have not only the intellectual ability via software, but also with machine learning in the hardware. And then the possibilities increase a lot. I cannot say how long this is going to take, because machine learning via hardware is going to be very complicated, because it involves studying materials perhaps for decades. So probably we're going to have tremendous developments of machine learning via software, and has such intelligent systems that may even help in developing the other parts, which will be machine learning via hardware and quantum computing, because quantum computing is also a big challenge, and it's not in the foreseeable future to have it used routinely. Whereas machine learning via software, the things that I showed to you today, they are already happening. So very soon we are going to have that interpretation of text, and then machines creating knowledge. And so even before we reach the situation of having machine learning via hardware, which is really going to be difficult.
It's like a long-term game for us to develop more and more related to the artificial intelligence. And
could you use the other microphone? Your microphone is giving a problem. I cannot hear properly. The other one seems to be better.
Hello, can you hear me right now?
Yeah, I don't know. Perhaps if you talk a little bit further from the microphone, because
okay. Yeah. How about now?
And how about the other microphone? The other one seemed to be better.
Sorry.
Or it may be interference from the microphone in the computer.
Okay, thank you so much for the session. I think we have a time constraint here, and we do believe that you already completely midnight in the Paulo, so we don't want to keep you for the time. So for the next, we will have a certificate of appreciation to you as our distinguished speakers for the international conference on advancement of technology on December 20 and 22 from Jakarta. So once again, thank you so much, Professor Osvaldo. It's really fruitful and insightful to us related to your topic. So
thank you very much indeed.
Yeah.
And I hope next time I'll be in Indonesia with you. So,
yeah, I'm looking forward to it, so we can meet you in person. Okay.
Thank you. Thank you very much.
Thank you. Thank you so much.
Have a good day. Thank you.